All right, Buenos Dias team, we're coming at you live from my kitchen with my toddler awake, so we're going to see how well this goes. We have the 2006 released MCQs for AP Physics C Mechanics. Let's get into it. Alrighty, Rue. We have, hi, a feral toddler on my lap. We're going to do our best. All right, so the questions are released on College Board. I'm not going to post them here because I have the test book. So this is my key. All right, so a box of mass M slides to the right on a horizontal surface, and a small cube also of mass M is inside the box. You're going to remember this question because it was probably the one where you're like, WTF am I looking at? This is horrible. Why would they do this to us? So part A, or determine an expression for the magnitude of the acceleration of the cube. Now this is one where people probably overthought it a lot. So for AI, we want to have our system just the cube. So the system, just the cube. All right, so we're going to draw our free body diagram. We have the weight of the cube. So good old mg. Friction is what is keeping our cube from falling to its death inside the box. And as the box is moving and slowing down, it is giving that normal force that our cube feels. All right, so this one is just wanting you to write Newton's second law. So sum of the forces in the horizontal direction for the cube. Sum of the forces in the horizontal direction. That's just going to be Fn to the left. So Fn is to the left, and that's going to be equal to ma. And if we rearrange for a, that means our acceleration is Fn over m. Now, if you really want to, you can slap that minus sign on there to say that we're going to the left. That's going to come out once we actually solve for the acceleration later, though. So whether or not you need that, because we're asking about the magnitude of the acceleration, so we don't care. So it's up to you if you wanted to include it or not. All right, for AII, this is the part where it gets tricksy. So we want to derive an expression for the normal force as a function of time t from t equals 0 to immediately before the cube reaches the bottom of the box. So this is the part where the normal force is changing as a result of the box slowing down because of that resistive force. So what we want to do here is we want to figure out what is the acceleration because these guys are accelerating together. And then we're going to shove that into this expression up here to solve for our normal force. So if we want to find the acceleration, so we're going to find the acceleration as a function of time as a result of that resistive force on the box, then we're going to stick it into our answer from part AI.
Wow.
Or stick it into our answer from part AI.
Oh.
Yeah. I know. So in this case, we want our system to be the box plus the cube. So there's my nebulous system, my box and the cube. We've got some FGs down. We've got some normals up. I don't care about those ones. This is normal with the ground. I care about this one, my resistive force. Okay? So in the x direction, the sum of my forces in the horizontal direction is only... All right, so we don't care about the weight of the system or the normal force of the system against the floor. We only care about the horizontal forces because that's what our acceleration is happening because of. That made no sense. Whatever. So sum of the forces in the horizontal direction, we have that resistive force. We got that negative BV rolling to the left. We're going to have the mass of our system times the acceleration of our system. They're accelerating together, and that total mass is block plus cube. Each of them is m, so that total mass is 2m. All right? Now, they did not give you a lot of room to solve a diffie q. That's not very nice of them at all. So now this is where we want to solve this diffie q. So we want to recognize that acceleration is dv dt. we're going to separate our variables. So I'm going to get all my v's on the right side, all my t's on the left side. So I'm going to get that minus b divided by 2m, multiply that dt over there. I'm going to divide my v over here. We need to integrate those with appropriate limits. So my time is going from 0 to some future time t before I hit the ground. My velocity, I'm starting at some initial velocity and I'm going to a future velocity v of t. That's really crunchy. I'm going to move that down. Yeah, that's better. Okay, so I'm going to some future velocity v of t. V of t. All right, let's integrate that bad boy. So if I do the left side, that's going to give me negative b over 2m with a t. If I integrate the right side, 1 over v integrates to a natural log of v. I'm going to evaluate that from v naught to future v of t. We're going to evaluate u from 0 to t too, my bad. So we get negative b over 2m times t. On the left side, we get the natural log of v of t minus the natural log of v naught. If you remember your log rules, I can slam them inside the same log by dividing them. Boom, boom. All right, to undo a natural log, I need to e both sides. So we're going to get e to the negative b over 2m times t is going to be equal to v of t over v naught. We're going to multiply him to the other side. Do, 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 do. Equals v of t. And there's my expression for velocity as a function of time. Cool. It's a decaying exponential, which makes sense. You're going to be slowing down because you have a resistive force. But I want acceleration. How's acceleration related to velocity? It's the derivative. So we need to take the derivative of that expression that we just found. Barf. Okay. So if I do that, my acceleration as a function of time, derivative of an exponential is itself. So e to the minus b t over 2m, and then multiplied by the derivative of the exponent. So that's going to give me a b over 2m with a negative sign. So that's telling me my acceleration is to the left, which makes sense. My net force is to the left. Last but not least, if we shove that back up into part A, normal force divided by m is my acceleration. So that means my normal force is just ma. So my normal force as a function of time, I'm going to take that whole acceleration, I'm going to multiply it by mass. That's going to cancel out my mass in this denominator here. So I'm going to get negative b v naught over 2 e to the negative b over 2m t. Yay, we did it! Phew! Okay, cool. That was part A. I and Aiii. We still have Aiii, which is the graph. So on our axes, below, we need to sketch the graph of the magnitude of the friction force. So this required you to remember that when I slip, so this is where I'm going to slip, that slip point is exactly where my static friction force gets overpowered by the force trying to undo my friction. In this case, looking at my free body diagram, that's going to be where my friction force is equal to my weight. So I'm going to slip when mu static times the normal force is exactly equal to the weight. Before that, my friction force is exactly what it needs to be to keep it still. Exactly what it needs to be to keep it still is equal to the weight. So this is going to be a straight horizontal line equal to mg until I slip. When I slip, remember that kinetic friction force is always exactly equal to mu times the normal force. But mu k is always less than mu s, so you're going to have a discontinuity here. And then after that, that normal force is a decaying exponential. So you're going to get a concave up graph here. Boom. That's part A. All right, for part B, we want to derive an expression for T crit in terms of NB, mu, S, V naught, and physical constants. So this is where we're going to take into account what we just said in our graph, is that when we slip, that's when our static friction is exactly equal to the weight. So we're going to use that to our advantage. We're going to plug in our expression for normal force. So mu static normal force. So mu static normal force, we are not going to include the negative sign in this case because I care about the magnitudes. We already took that into account when we wrote this. It's going to be mu static b v naught over 2 e to the negative b over 2m times t. That's going to be equal to the weight. So let's solve for t. So I'm going to get all this stuff over here. So that's going to give me 2mg over mu static b v naught with e to the negative b over 2m times t over here. To undo an exponential, we're going to natural log both sides. So that gives me negative b over 2m. T is equal to the natural log of 2mg over mu static b v naught. And then get all this constant stuff over here. So I'm going to multiply my 2m over with my b. Natural log, I'm going to add parentheses this time because just to make it clear. Ba-na-na-na-na-na-na. Boom. There's our time. Cool. Or TC, if you will. Ta-da! So hopefully you managed to scrape up some points on that. Fingers crossed. We'll hit part B in just a sec. Or question 2 in the next video.